Welcome back to Computer Graphics and Visualization subject, Module 5. Right? We were discussing curves. Again, today also we'll continue with the curves. Right? We'll try to elaborate different type of curves used for computer graphics, animation, and drawing complicated objects. Right? Today we'll discuss Cubic-Spline interpolation method. Cubic-Spline interpolation method. Right? Again, there are different type of curves are available, but among those, these type of curves are very effectively used in computer graphics. This class of spline is most often used to set up paths for object motions or to provide a representation of an existing object or drawing. But interpolation splines are also used sometimes to design object shapes, right? This is the advantage over other curves, right? Quadratic curves and other curves, higher order curves, whatever higher order curves or higher order shapes, if you take, those are very complex, then they may not give accurate or approximations for motions or represent existing objects, right? That's why you'll prefer cubic spline, cubic type of curves, right? Cubic type of curve. By cubic polynomials offer a reasonable compromise between flexibility and speed of computation. As I told, if you go for higher order, then the computation is very high. Right? If you go higher order, means higher than cubic or some other than that cubic order, if you go higher order, definitely the complexity will be increased. For complexity will be increased. Then if you go by lesser order, than the cubic, right, quadratic and all those things, then you will not get more flexibility. That is the reason most preferred curves are cubic curves, right? That's why you prefer cubic curves, right? Cubic splines require less calculations and storage space, and they are more stable. If you compare other type of curves, higher order curves and lesser, other than cubic, higher means most time higher order curves, cubic splines require less calculations, complexity is very less, and storage space, they require less storage space, and they are more stable. Means they will give approximate answers whenever you are doing any calculation. That's why this type of curves we will prefer, that is cubic spline. Then compared to quadratic polynomials and straight line segments, cubic splines are more flexible for modeling object shapes. As I told, if you go lesser order curves, that is a quadratic at that time, or straight line segments, if you go straight line segment, then you will not get smooth curves, you will not get smoothness in the object design, right? That's why they are not flexible for modeling the object shapes. Means if you want a curve shape, if you go by straight line, you may not get a curve shape if you go by straight line segment, right? Again, if you go by a quadratic equation, then flexibility will be not there. Means if you want to adjust your shape, it is very difficult for adjusting. That's why flexibility is not there if you go lesser order. Then if you go higher order, complexity will be increased. If you go higher order, the higher order plus curves, then complexity is more. If you go lesser, you will not get a flexibility. That's why ideal curves are cubic curves, right? Then how the curves will be drawn in OpenGL or in computer graphics? How curves will be drawn? Given normally curve will draw by using control points. Normally you will prefer control points. Depending on the control points, you will draw the curves, right? That are given a set of control points, means they will give a set of control points. Those control points are nothing but x, y, z. If it is a 3-dimensional, if it is a 2-dimensional, x, y, then those are called positional vectors. Means each position they will give some control points. Then by using those control points, we have to draw the curves, right? That is a funda behind this one. Among that, first we will discussing cubic splines, right? Cubic interpolation splines are obtained by fitting the input points with a piecewise cubic polynomial curve that passes through every control points, right? Here, cubic spline curves, how we are drawing cubic spline curve means you have been given with a set of control points. then you make use of those control points, then draw that curve using piecewise, not from first to last directly. We will not draw that in below figure. You can see there are n number of control points, that is P0 to P1. They have been given with n number of control points, P0 to Pn. Then by using those control points, we have drawn that curve. We have drawn that curve means nothing but we have not drawn that direct curve directly from P0 to Pn. We will draw piecewise. We will draw piecewise, like piecewise nothing but P0 to P1 one curve, then P1 to P2 other curve, then P1 to P3, then P3 to P3. Like this we will draw piecewise. By boundary conditions we have to apply the boundary conditions, all those things. By applying those boundary conditions we have to draw this. That is what the cubic means. Again, interpolation is nothing but if that curve follows all the control points, if that curve follows all the control points, then that is interpolation. Means whenever you are drawing a piecewise, there may be chances that one end of one piece may not coincide with other end of other piece. That's why if that is the case, then those are called different approximation and all those things, right? But interpolation is nothing but if your entire curve passes through all the control point exactly and all the control point, that is called interpolation, right? Meaning of interpolation is nothing but when you are drawing a piecewise, you have not drawn the curve entirely from starting point to end point, you have drawn that curve by piecewise, right? When you are drawing this piecewise, the curve whatever you are from total curve, that is a P0 to Pn, P0 to Pn. If the P0 to, when you are drawing P0 to Pn, that curve, if that curve passes through all the control points exactly and all the control points, that is a positional vectors, those are positional vectors, then that is called interpolation curve, right? That is what through the every control point, right? Suppose that we have n plus 1 control points specified with the coordinates. The same example whatever I explained, that means suppose that we have n plus 1 control points specified with coordinates. Each control point has x, y, z, as I told. Pk, in general, if Pk is a one control point, it has x value, it has y value, it has z value, right? Where k value varies from 0 to n. Means there are total n control points. A cubic interpolation fit of these points is like this. Means P0 to P1 one curve I have drawn, P0 to P1 one piece I have drawn, then P1 to P2 I have drawn, then they automatically they are joined. Again now they are joined, that is again blending functions, all they will take care. Means again the boundary conditions we have to apply, then we have to check boundary conditions, depending on that we will do that one. Then P2 to P3, P3 to P4, like this we will start drawing piecewise, then we will complete that entire curve, that is P0 to Pn. This is what the cubic spline. Then we can describe the parametric cubic polynomial, right? Cubic polynomial means cubic parameter is nothing but the order of that polynomial is 3. The order of degree of that polynomial is 3. That is called a cubic polynomial. That is to be fitted between each pair of a control points with the following set of equations, right? The cubic polynomial is nothing but if the polynomial has the degree 3. Any polynomial, if that polynomial has the maximum degree 3, then that is called cubic polynomial. If any polynomial has degree 2, then quadratic polynomial, right? Like that. Cubic means degree is minimum degree is 3. That is to be fitted between each pair of control points with the following set of equations. Means x, y, z. Always if you are taking a 3-dimensional, then there is at each point, each positional vector, there is a x, there is a y, there is z, right? Then polynomial with parametric equation, again parametric, that is x of u. X depends on u, where u varies from 0 to 1, right? If u varies from 0 to 1, means this is a parametric equations. X of u equal to this is a quadratic cubic equation, that is means cubic polynomial, that is in general ax cube plus bx square, like that, right? That is x a cube, like that. That is what ax u cube plus bx u square plus cx u plus dx. This is a cubic polynomial with respect to x. Similarly with respect to y, ay u cube plus by u square plus cy u plus dy, right? With respect to z, again same, az u cube plus bz u square plus cz u plus dz. You have to solve for each and every point. You have to solve these 3 equations depending on u. U varies, where u varies from 0 to 1, right? U varies from 0 to, means at one end of your curve u is 0, at other end of your curve u is 1, other end of your curve u is 1, then u will varies between 0 to 1. Depending on u value, then you will get x, y, z if you calculate these equations, right? For each of these three equations, we need to determine the value for the four coefficients, that is a, b, c and d. For each of these three equations, we need to determine the values for the four coefficients a, b, c and d. In the polynomial representation, for each of the n curve sections, between the n plus 1 control points, means if you have n plus 1 control points, you will get n curve sections. You have to calculate these for all n curve sections, or n polynomial representation for each of these n curve sections between n plus 1 control. Means if you have n plus 1 control points, you will get n curve sections. For each n curve sections, you have to calculate these x, y, z, right? Then do this by setting enough boundary conditions. Then as I told, how to do this one, you have to set the boundary conditions, then you have to check boundary conditions. Depending the boundary conditions, we will decide whether that is going in correct path or not, right? Means normally we have to set these boundary conditions to check whether the two curve sections are going in right direction or not, because when you are joining a piecewise, the joining may be different, or they may not be joining at same point. Means normally when you are joining a piecewise, the first piece last point and second piece first point must start at same point, right? When you are joining a piecewise, first piece of curve section last point must end, means end point of first piece and start point of next piece must be at same point, right? Means to check these properties, we have to set the boundary conditions at the control point positions between the curve sections, so that we can obtain numerical values for all the coefficients, right? By setting this, right? Then there are different type of cubic splines, right? First one is natural cubic spline. First type is natural cubic splines. Then means they have different properties. Depending on those properties, they are different cubic splines, right? First one is natural cubic splines. One of the first spline curves to be developed for graphics application is the natural cubic spline, right? Then this interpolation curve is a mathematical representation of the original drafting spline. This interpolation curve is a mathematical representation of the original drafting spline. Okay. As I told, what do you mean by interpolation? Interpolation means nothing but all your entire curve from starting control point to last control point, it has to go through all the control points. How many control points you have? It has to intersect all exit, means it has to pass through exactly on those control points. That is interpolation, right? We formulate a natural cubic spline by requiring that two adjacent curve sections. We formulate a natural cubic spline by requiring that two adjacent curve sections have the same first and second parametric derivations, right? First order derivation, I hope you know first order derivation, second order derivation, like that. Means the adjacent curve sections have the same first and second parametric derivatives at their common boundary, right? Means when they are joining, first piece and second piece, when they are joining, the first order and second order derivative at that point must be same, right? They must satisfy this condition. What is the condition? Boundary condition. First and second parametric derivatives, first order derivation, second order derivation at that point, at the means first piece and second piece starting point control, that is the control point. First piece end point control point and second piece starting control point, they must satisfy this condition. What is that? First order derivation and second order derivation of those points at that point must be same, common boundary, right? Then thus natural cubic spline here, this is called C-square continuity. That is in general we will call continuity. Means we have to check whether they are following the continuity conditions or not. Means if it is going in right direction, if means assume that you are moving from left to right, in first piece you are moving from left to right, then again in second piece also you have to move from left to right. It should not happen that the second piece must move from right to left, right? That is a continuity you have to check. How to check the continuity? That continuity is checked in natural cubic spline. First order derivative and second order derivative at the common point, must be same, right? This condition means first and second parametric derivative at the common boundary must be same, right? Then if we have n plus 1 control points, then we have n curve sections, and I told then we will have n curve sections with a total of 4n polynomial coefficients to be determined, right? How many coefficients you have to determine? 4n polynomials. When you have n plus 1 control points, there are definitely total n curve sections, means n pieces you will get. Each piece has 4 coefficients, that is x has a, b, c, d, y has a, b, c, d, c has a, b, c, d. Then total how many coefficients you have to calculate? 4 into n. You have to calculate 4 into n control points. You have to coefficients you have to determine. At each of the n minus 1 interior control points, you carefully go through these lines. At each of the n minus 1 interior control points, we have 4 boundary conditions. At each of the n minus 1 interior control points, we have 4 boundary conditions. Right? That is first order to second order 2. That is each control point, definitely each interior control points we have 4 boundary conditions, right? One from the one piece end and another from the other piece starting, right? Again there is a first order derivative, second order, that's why 4 boundary conditions has to be satisfied every all n minus 1 interior control points, right? How 4? First order derivative 2 means first piece end point, first order derivative, then second piece starting point, first order derivative 2, right? Then first piece end, second order derivative, second piece starting, second order. There are 4 boundary conditions, like this 4 boundary conditions. The 2 curve sections on either side of the control points, must have the same first and second parametric derivations at that control point. As I told already, I have told this one, means at each 2 curve sections on either side of the control point, must have the same first and second parametric derivatives at that control point, and each curve must pass through that control point. Again that curve must pass through control, that is interpolation. As I told, interpolation is nothing but that curve must pass through that control point. Then each n minus 1 point must have 4 boundary conditions, that is first order to second order 2 on each side, means end and starting, right? That is what the meaning of that line. This gives us total 4n minus 1 equations. To be satisfied by the 4n polynomial coefficients. Why 4n minus 1, 4n minus 4? Because last points means starting point, that is P0 and Pn they don't have 4 boundary conditions. That is a separate, right? We will go to that point. That's why this gives us 4n minus 4 equations to be satisfied by the 4n polynomial coefficients, right? Total each n minus 1 interior control points, you have to calculate 4n minus 4 equations to be satisfied by the 4n polynomial coefficients. If there are 4n polynomial coefficients, then 4n minus 4 equations you have to calculate 4n minus 4 equations. Because why minus 4 means end points, means that is a P0 and Pn have different boundary conditions. P0 and Pn have different boundary conditions, right? Then we obtain an additional equation for the first control point P0, as I told. Means why this minus 4? Minus 4 is we obtain an additional equation from the first control point, that is a P0, the position of the beginning of the curve, and the another condition from control point Pn, which must be the last point on the curve. That's why we have subtracted minus 4, means they will get 4n minus 4 equations, right? Because P0 and Pn are different. P0 and Pn conditions, boundary conditions are different. We must be the last point of the curve. Then however, we still need two more conditions to be able to determine values for all the coefficients. However, we still need two more conditions to be able to determine values for all the coefficients, right? Means 4n minus 4, 4n minus 4, then these two, right? That's what that is the meaning. Means however, we still need two more conditions to be able to determine values for all these coefficients. One method for obtaining these two additional, that is P0 and P0. There are again two methods to get the boundary conditions for this P0 and P1. Again, because P0 and P1, again first point has to pass through P0, second last point has to go through Pn, right? Again you have to check condition, boundary conditions. Again there are two methods to calculate these boundary conditions, right? One method for obtaining the two additional conditions is to set the second derivative at P0, and Pn equal to 0. One condition means second derivatives at P0 and Pn equal to 0. One condition, you set second derivative at P0 and P1 equal to 0, right? If both are equal to 0, then that is boundary condition, means nothing but the first point is started at first control point, then last point is ending at last control point, right? One more method is, another approach is to add two extra control points, like how we have done. Means in previous how we have taken for each control point we have taken four equations, four conditions, right? Like that also here also what you do, another approach is to add two extra control points, that is a dummy control points, one at each end of the original control point sequence. One at each end means one condition extra control point you add at beginning, one more control point you add at end, one more control point you add at end, that is a dummy points, right? Like this. That is, we add a control point labeled P minus 1, control point labeled P minus 1 at the beginning of the curve, and the control point labeled Pn plus 1 at the end. Means additional dummy 2 points we are adding. Means if you have four control points, then by adding these two control points you will get 6 control points, but these two control points are a dummy, just to calculate the boundary conditions, right? These are dummy. Then all the original control points are interior points, and we have the necessary 4n boundary conditions. Already you know that we have the necessary 4n boundary conditions for interior, right? If the position of any of the control points is altered, the entire curve, again now in this case total boundary conditions are 4n minus 4, but if you add again these also, total you will get 4n boundary conditions here, 4n boundary conditions, right? Because again for starting and end also you added 1, that is again those will become 2, means again 2 means again everywhere first order derivative, first piece end, first order derivative, second piece start, right? Then second order derivative, first piece end, then second order derivative at second piece start, first piece end and second, like that you will get total 4n boundary conditions. But if you go for this natural cubic spline, then we have disadvantage here. What is the disadvantage of this? If the position of any of the control point is altered, afterwards if you want to change the shape of the curve, then you want to change the any one control point position. If you change the any one control point position, the entire curve is affected. This is called a global control points, means they are controlled by globally, right? If you change any one control point just to make change of the shape of that curve, then the entire curve will be affected. This is the disadvantage of this. Thus natural cubic splines allow for no local control, means you cannot control locally. Means, so for example, you have drawn one piece from P1 to P2, you have drawn one curve from P1 to P2, but afterwards you want to change the shape between P1 to P2, curve. It is not possible here. If you want to change locally, it is not possible. If you change any control point in this natural cubic spline, the entire curve will be affected. That is what the meaning. This natural cubic spline allow for no local control, so that we cannot restructure part of the curve. You cannot restructure part of the curve without specifying an entirely new set of control points. Means even though you want to change, only you want to make a change in one piece of curve, because this is a group of pieces. Means how you have drawn entire curve, you have drawn curve by piecewise. You have drawn entire curve piecewise, but you want to change shape of one piece, it is not possible. Even though if you want to change the shape of one piece, you have to specify entire new sets of control point. You have to set entire new sets of control. This is the disadvantage of this. To overcome that disadvantage, we have the one more spline curve, that is Hermite interpolation. That is called Hermite interpolation, right? Hermite interpolation. The Hermite spline, named after the French mathematician Charles Hermite, right, is an interpolating piecewise cubic polynomial with a specified tangent at each control point. Here we are specifying tangent at each control point. Here we are specifying tangent at each. Tangent means directional vector. Tangent means directional vector, means which direction the curves are moving. That is tangent. We are setting tangent at each control point, right? Is again interpolating. Again every piece of curve has to go through it, that control points. Every piece of your curve has to go cross through control point, right? Polynomial with a specified tangent at each control point. We are specifying a tangent at each control point just to check the continuity, whether they are following the same path or not, right? Then unlike the natural cubic splines, Hermite splines can be adjusted locally because each curve section depends only on its endpoint constraints. Only on its endpoint constraint, right? That's why here means each piece is only depends on endpoint constraints, right? That's why here you can adjust. The local adjustment will be there. Means if you want to change the shape of one piece between P2 to P3, you have already drawn one curve between P2 to P3. One piece you have drawn from control point P2 to P3. Afterwards you want to change the shape between P2 to P3. Whatever earlier you have drawn, you don't want that shape, you want to change, that is allowed here, right? Because the control endpoints are controlled only within the endpoints. This plane is control depends only on the endpoint constraint, right? That is, if P of u represents a parametric cubic point, if P of u represents a parametric cubic point, that is a control point function for the curve section between control points pk and pk plus 1, pk and pk plus 1. One P of u parameter represents a parametric cubic point function for the curve section between control points pk and pk plus 1, as shown in the figure next, like this. pk plus 1, that is a P of u, one control point with the parametric equation, that is x of u, y of u, z of u. Then the boundary conditions that defines this Hermite curve section are, then the boundary condition that defines this Hermite curve sections are P of 0 equal to pk. P of 0 equal to pk means P of 0 is nothing but pk, means when u is 1, when u is 0, at that time, at this point u is 0, at this point u is 0, that is a pk. If u is 0, then you are here, right? When u is 1, then you are here. When u is here, you are here. Then this first derivative of this, that is p dash of 0. First derivative of this is dpk. This first derivative, right? First derivative of this is dpk. Then first derivative of this is dpk plus 1, right? These four conditions this has to satisfy, right? This has to satisfy, right? With dpk and dpk plus 1 specifying the values for the parametric derivatives. The values for the parametric derivatives, slope of the curve at control points pk and pk plus 1 respectively. Means that is a tangent values. Slope of the curve will be specified by dpk and dpk plus 1 respectively at pk and pk plus 1, right? This boundary condition that defines this Hermite curve, right? That is, every point has to satisfy these four parametric boundary conditions, right? Then we can write the vector equivalent of equation 8 for this Hermite curve section as, we can write the equation, we can write the vector equivalent of equation 8 for this Hermite curve section as, equation 8 is this, right? We can write that one as here, P of u equal to ae cube plus bu square plus cu plus d, where u varies from 0 to 1 plus u varies from 0 to 1, right? That is P of u equal to ae cube plus bu square plus cu plus d, right? Where the x component of P of u is u of u, means if you go by x and y, because everywhere any point, if you take any point on that curve, which as per u value, then every curve has x, y, z. If you take x component p of u, then that is ax u cube plus bx u square plus cx u plus dx. Similarly y and z. Already we have written that one like this here, right? Already we have written like this, right? Then components. The matrix equivalent of above equation is, if I write matrix equivalent of above equation is, then u cube u square u1, that is u cube u square u1, that is p of u, right? Then a b c d. If I write this in the matrix equivalent format, then u cube u square u1, that is u cube u square u1, then coefficients of these are a b c d, right? Then, and the derivative of the point function can be expressed as, means derivative, this is what the point, right? Then derivative of this first order derivative of u cube is, u cube is 3u square, means derivative of u cube is 3u square, derivative of u square is 2u to the power 1, right? Derivative of u is 1, derivative of 1 is 0, that is first order derivative, right? du cube by dx, or du cube by dx, du square by dx, du by dx, du1 by like this, right? First order derivative, that is 3u square 2u, means first order derivative of p dash of u, because first order means there are four control points, that is four boundary conditions, p0 p1, then derivative of first order derivative of p0, then first order derivative of p1, right? This is the what, then a b c d. Substituting endpoint values 0 and 1 for parameter u into the preceding two equations, then substitute 0 and 1 at these equations, we can express the Hermite boundary conditions 9 in the matrix form. Means condition 9 means, if you can express that in previous equation, means that is equation number 9, if you substitute that one, that is pk, that this pk here, pk, I hope here, if you substitute this one, then that is pk is, if I substitute, means pk at 0, 0 is nothing but u is 0, means 0 0 0 1, 0 0 0 1. In this means x, if I take this one 0, p of 0 0 cube 0, right? 0 square 0 into something 0, then d is 1, right? D is 1, that is we have taken here, we have substituted. Then 1, pk plus 1 at the end, other point u is 1, right? Again if I take here in this 1 cube 1, then 1 square 1, 1 into 1, then 1, this is what, this 1 1 1. Then here in this again if I substitute 0, in this if I substitute 0, 0 square into 0 0, 0 into 0, then 1, that is 1, then this is 0, right? Then pk plus 1, then other end is 1, other end u is 1, starting end u is 0, that is 1 cube 1 square into 1, that is 3, then 1 into 2, then 1 into 1, right? Then 0 0, this is what, then this is a b c, means substituting endpoint values 0 and 1 for parameter u into the preceding two equations, we can express the Hermite boundary conditions 9 in the matrix form. Means we are written right, that is pk at 0, pk plus 1 at 1, first order derivative of pk is 0, then first order derivative at pk plus 1 is at 1, right? This is what matrix form. Then solving this equation for the polynomial coefficients, we get, solving this equation for the polynomial coefficient means we have to solve for a b c d, we have to solve it for a b c d, right? Then if I take ABCD matrix this side, then this will become inverse, that is 0 0 1 inverse, then pk plus 1 dpk means simply I have taken, we are solving this one for this, that I have taken, means this I have transferred to left side, that automatically that matrix become inverse. that matrix become inverse. Then inverse matrix, if you calculate inverse matrix, then how to calculate inverse matrix, I hope you know. That is 1 by determinant of this matrix into adjacent adjoint of this matrix. How to calculate inverse of matrix? Inverse of matrix is 1 by determinant of the matrix, which matrix you are calculating inverse, then into adjoint of this matrix, adjoint of this matrix, that you will get inverse of this matrix. This is the inverse of, if I convert this matrix into inverse, then I will get this, right? Then dpk. Then this I will call it as mh, that is Hermit matrix. This I will call it Hermit matrix, right? This takes care of the continuity. This matrix will take care of continuity of the piecewise drawing, right? This I will replace with mh, right? pk plus 1. Then where mh is Hermit matrix, is the inverse of the boundary constraint matrix, Equation L1 can thus be written in terms of the boundary conditions as equation 1. L1 can thus be written in the boundary conditions as P of P equal to U cube U square U1 mh. mh is Hermit matrix. pk plus 1 dpk plus 1, right? This is just rewritten the matrix, that is L1, equation L1 we are rewritten, right? That means Hermit matrix. This matrix will take care of your continuity and all those things, whether continuity and whether all the points are intersecting at control points or not, right? Finally, we can determine expressions for the polynomial Hermit blending function. This is again the Hermit curve or blending function. This is also called Hermit curve or blending function. Polynomial Hermit blending function, that is HKU, right? For k equal to 0, 1, 2, 3, by carrying out the matrix multiplication in equation 15. Carrying out matrix multiplication equation and collecting coefficients for the boundary constraints to obtain the polynomial form. Means if I multiply these matrix, if I multiply those matrix, these matrix, if I start multiplying these matrix, then what I will get, right? Here, if I multiply that PU, that is PK, first point is a PK, then 2U cube, this is 2U cube, right? 2 this matrix, then this is U, right? This is what mh is this matrix, then this is what 2, this is U cube, then mh has here 2, that is 2U cube, right? Then minus 2U cube, then minus 3U cube, that is minus 3U cube, because row into column we are multiplying. This U cube, that is a row, this is a column, then minus 3U cube, minus 3U square, right? Then plus 1, that is pk, then pk plus 1, that is minus 2. Means just we are multiplying this matrix and this matrix values. We are multiplying this matrix values and this, right? Just we are that is mh matrix values already here we have. mh matrix value already we have. Directly I am multiplying here, right? Then that is pk minus u cube plus 3u square, then plus dpk u cube minus 2u, then this. Then we will replace this 2u cube minus 3uk, then this, we will replace that one with h0, h1, h2, h3, that is Hermit h1, Hermit h2, h like this, right? Then pk h0 of u, then pk plus 1 h1, then pk dpk h2, then dpk plus 1 h3, right? Below figure shows the shape of the 4 Hermit blending functions. The below figure shows the four Hermit blending functions, right? Then this is h0 of u, right? h1 of u, right? Then h2 of u, then h3 of u. These are the four blending functions graphs, right? Then Hermit polynomials can be useful for some digitizing applications. Hermit polynomials can be useful for some digitizing applications where it may not be too difficult to specify approximate the curve slopes, right? Hermit polynomials can be useful for some digitizing applications where it may not be too difficult to specify or approximate the curve slopes, right? But for most problems in computer graphics, it is more useful to generate spline curves without requiring input values for curve slopes or other geometric information in addition to control points coordinates, right? Means here also we have advantage and disadvantage. Depending on that, depending on which type of application we are using, either we go for this or we go for previous one, right? This is regarding the cubic spline curves, right? In next class, in next video, we will start discussing Bezier curves.